Hi everybody, as promised, we're now going to walk through the math for a 2 by 2 chi-squared analysis. Let's see how that goes. Okay, just like the last video, I'm going to use the same example, but now actually put in some numbers. So let's imagine that there's somebody named Dr. K. They want to see if this new medication is actually effective at preventing heart attacks. And so you can just ignore sort of the research methods portion of all this. Just imagine that's relatively sound, all this kind of stuff. But this is essentially what they're trying to do is they want to give everybody, randomly assign them to either the placebo condition or the medication condition, and then see if they have a heart attack over we'll say the next 6 months or whatever. It doesn't matter for our purposes. However, of course, in your research methods course, that would very much matter. Okay, so once again, we have two variables. One of them is whether the person had a heart attack, and the other one is which intervention they received. And both of those variables each has two levels to them. In other words, they could be two possibilities, two values. The heart attack condition could be yes or no. It can't be middle, like in between, like you sort of had a heart attack, nothing like that. And the intervention also same thing. Everybody received either the placebo 100% of the time or the medication 100% of the time. Okay, so this is therefore a 2 by 2 chi-squared analysis. 2 by 2 because there are two levels in the first variable and two levels in the second variable. That makes it a 2 by 2 chi-squared analysis, as we covered last time. Now, of course, our null hypothesis should reflect the theory that the intervention has no effect whatsoever on whether the person has a heart attack. Now, again, really quickly, we're assuming that it's the intervention that is going to lead to the heart attack, right? You can't always do that with a chi-squared analysis, of course, because it's similar to a correlation, but we'll just plow forward in this case and assume that that's probably true because chronologically the intervention came before the heart attack. It's probably not the person having a heart attack determining which medication they got, okay? Anyway, so our null hypothesis then is it doesn't matter which intervention you get, you have the same likelihood of having a heart attack, okay? So that would look like this in symbols. Of course, the null hypothesis or default hypothesis is that the probability of having a heart attack, yes, having a heart attack, after having had the placebo is the same as the probability of having a heart attack after receiving the medication, okay? That's basically how we do that. The alternative hypothesis is, of course, that it does matter, and so there's something wrong with our null hypothesis. Because we have only two variables and two levels for each variable, we can just summarize it like this and say, actually, that's not true. They have different probabilities. Now, we're not sure which direction it goes. We don't know. Maybe actually it is better and safer to not take the medication in the first place. That's kind of, I mean, hopefully you've gone through several trials before going to human subjects in this case. But that's certainly possible. So if we obtain a statistically significant chi-squared value, that means that we can reject our null hypothesis and we can accept that this one appears to be best supported by the evidence. Now, of course, one quick note is if you have more than two levels for one of your variables, you can just ignore this and say that the alternative hypothesis is that the null hypothesis is not true. Okay, just to summarize all of that. So now let's imagine that these are the data that Dr. K found. So in other words, 23 people received the placebo and they then had a heart attack within the study's time frame. 57 received the placebo and did not have a heart attack during the time of the study. 12 people received the medication and had a heart attack, and then 68 people did not have a heart attack after receiving the medication. Okay, now of course what we're doing here with this chi-squared analysis is saying, is the proportion of this to this different than the proportion of this to this, essentially? That's basically what we're looking at here. Now I'm going to show you how we can calculate that, of course. That will be the way that we calculate our expected cell frequencies or expected cell counts. It's the same thing. So in other words, we're going to calculate what we would expect to have seen if the null hypothesis were indeed true. All right, and this is what that looks like. So all we do is, of course, have to calculate the totals for the rows and the columns in our table. So this is the same table that I had before, but I've just added in a new row and a new column so that we can have the totals. So obviously 23 plus 57 is 80, and I told you that Dr. K had apparently even assigned people equally either to the placebo or medication group. Random assignment doesn't always mean equal assignment, right? Anyway. And then same thing here, 80 people total received the medication. Now, 35 people total in the study had a heart attack within the study's time frame, and 125 did not have a heart attack in the total time frame. Now, there were also 160 total people in the study. Okay, so n equals 160. All right. Now, this is important again, just really quickly. We talked about it in the previous videos I was introducing this, but the point here is that we can't just assume that 25% of the people would end up in any one of these cells. That would be silly because there was a lower likelihood of having a heart attack than not having a heart attack in the first place. And so therefore we have to take that into account. We can do that easily mathematically, and I'm going to show you how to do that right now. So of course I introduced this equation to you last time. It's very straightforward. All we do is we take the cell's column total, multiply it by the cell's row total, and then divide by the total number of observations. So of course in our circumstance, all we're going to do here is take, for example, the column total. Well, okay, let me start here. If we are interested primarily in the people who received the placebo and then also had a heart attack, we're looking at this cell. We'll call it cell A. So what we're doing is taking the column total for that, the total number of people who had a yes heart attack, and then we're going to multiply it by the total of people who received the placebo. Then we're going to divide it by the total number of observations, which was 160. So let's go ahead and do that. Okay, so as I just said, all we're going to do here is plug in everything to the equation. So what we start off with is everybody in the yes column was 35, right? We had a total of 35 people who had a heart attack. We're going to multiply that by the total number of people who had the placebo, then divide that by the total there. So of course that gives us 35 times 80, which is 2,800. That divided by 160, of course, gives us 17.5. So what we're saying is, if the null hypothesis were true and which row you fell into didn't matter, didn't have any effect on which column you fell into, we should have expected to see 17.5 people have the placebo and then get a heart attack. Okay. Now let's plug that into a new table so that we can keep track of all of this interesting information. Okay, so all I've done here is I've added on a second table, or these don't even have to be the same table. I've just put them here for fun, just so we can keep track of this, right? We want to make sure that we're clear. So I've labeled this the expected cell values. That's as opposed to our observed cell values, okay? So our expected cell frequency or cell value for the people who received the placebo and had a heart attack was 17.5, as you can see right here. I just took our math from the previous one, plugged it into our table. I'm going to do that for each of the other values because we have 4 total cells here, 1, 2, 3, 4, and we need to come up with the expected cell values for each of these. So if we do this now for the second cell, or cell B we could call it, we're taking the people who received the placebo and did not have a heart attack. So now what we're doing here is we're taking the column total, which is 125, because that's how many people did not have a heart attack. We're multiplying it by the 80 people who received the placebo. Now, of course, that gives us 10,000. 10,000 divided by 160 is, of course, 62.5. So we just plug that right into here in our expected cell frequencies. Now you'll notice here we actually don't have to do any more math if you think about it, because we're now going to start using the same values into these equations, right? Even though there were fewer people here who received the medication and then had a heart attack, we're still using the same column and row information. And so actually we don't need to really worry about this too much going through the math. It's the same 35 times 80 divided by 160, which of course gets it to 17.5. Plug that right in. And then we'll do the same number, of course, for the people who received the medication but did not have a heart attack. That, of course, looks like this. Again, it's the same information, 125 times 80. Now, this is not always true because sometimes you'll have a different number of people who were assigned to the placebo group and a different number of people who were assigned to the medication group. So we're doing this only just because these both have the same numbers. It doesn't change any of our values here. So, of course, we get the same value for the people who received the medication but did not have a heart attack, which is 62.5. We just plug that right into our table. Now that we can keep track of both our observed cell values and our expected cell values, or observed cell frequencies and expected cell frequencies, we can now calculate our chi-squared value. Now again, we use the same equation as we've used before. So let's take a look at that. Here's the same equation that we've used every time we've calculated a chi-squared analysis. The only difference here was that we needed to calculate our expected cell frequencies in a different way than we had if we had only one variable. Okay, so if I use all of these, of course, I'm just going to plug in the observed cell frequency for cell A, which was the placebo group with a yes heart attack, and then subtract the expected cell frequency for cell A, which was the placebo group with a yes heart attack. 17.5, okay? And then I'm going to do the same thing for all of the other cells. Of course, the way that we do that is like this. You can plug all of those values in and you'll see here. So this was everything for cell A. 23 was the observed cell frequency and 17.5 was expected. So that goes both places. Cell B, of course, is 57 observed, and then we expected 62.5, so that goes both places. This is cell C, which is 12 observed, 17.5 expected. And of course, cell D, which was 68 observed, 62.5 expected. Now we just need to simplify. So here's the same equation with all of our values plugged in. All we do is simplify everything. Of course, what we do is we start in the numerator. The first thing that we have to do is what's in the parentheses, of course. Order of operations dictates that. So of course, we do all of our subtractions and we get, of course, 5.5 or negative 5.5 for every one of those. Now again, the little trick that I showed you before, of course, still applies, where if you just ignore the squaring for a moment and just add a cross there, you'll notice that this does equal 0. That has to be true for any chi-squared, unless of course you did any sort of rounding up here. Then it'll be ever so slightly off of 0. But this of course is true. 5.5 minus 5.5 is 0, and then another negative 5.5 plus 5.5 is also 0, so you get a total of 0 across those numerators. Now, of course, that doesn't help us with our chi-squared. It just shows us that we're on the right track, where we haven't screwed up our math yet. Okay, obviously what we do is square then. 5.5 squared is 30.25, so is negative 5.5, and so we just get the same numerator all across the board there. Okay, now of course what we do is we divide, and we have different denominators, so why don't we divide first and then we'll add a cross so that we don't mess anything up. That of course looks like this. 30.25 divided by 17.5 is 1.73, and of course we do that twice. We don't need to do it again over here. We'll just plug in the value. 30.25 divided by 62.5 is of course 0.48. I've rounded ever so slightly, okay, but that's all right. Okay, and of course we just add those across and we get a total chi-squared value of 4.42. Now of course, hopefully you know the drill at this point if you've been following these videos in sequence. We need to find the degrees of freedom. Now when we have two variables, this is different from the one variable chi-squared. When we have two variables, this is how we calculate the degrees of freedom. We take the number of levels that there were in one of the variables and subtract 1. We multiply that then by the number of levels in the other variable minus 1 in parentheses, as you can see. So of course in this instance we had two levels of variable A, which was the medication or the intervention, and then two levels of the variable B, which we're calling B, but it doesn't really matter. That was of course whether you had a heart attack or not. And of course 2 minus 1 times 2 minus 1 is the same as 1 times 1. 1 times 1 is of course 1. So we have 1 degree of freedom for our chi-squared analysis. Now of course Appendix E, as we've gone over before, if you're using my textbook, will show you that the critical value for a chi-squared analysis with 1 degree of freedom is 3.84. Once again, what that means is that is our lowest threshold for statistical significance. A chi-squared analysis with only 1 degree of freedom needs to be at least 3.84. The value of the chi-squared needs to be at least 3.84 before we can say that it was statistically significant. So of course in this instance, our chi-squared value that we obtained was 4.42 using the data that I gave you that are entirely made up, by the way. And 4.42 is of course larger than 3.84, so therefore we have statistical significance. We can reject the null hypothesis that said it didn't matter which row you fell into to shape which column you fell into. It turns out it actually does matter. So now let's talk about how it matters. Now, of course, at this point, as we've talked about a little bit before, what we can do is take a look where our biggest discrepancies were. So we go back to our math, that point right before we added up all these values to get 4.42 or whatever it was, and we can see that the biggest discrepancies were both in these locations. Now that was for cell A and for cell C, which was everybody in the yes column. In other words, we saw a biggest discrepancy among the people who did have a heart attack than we expected. We saw some discrepancy in the no's column as well, but that's fine. In fact, we can then inspect that and take a look at our expected and observed and see, oh, look at that. We expected to see 17.5 people have a heart attack getting the placebo, but it turns out it was more than that. 23 is bigger than 17.5. So we saw more than we expected with the placebo, but we saw fewer than we expected if people had the medication. So at this point now we can conclude it looks like our medication was making a difference here, and it was making a meaningful difference. At this point we should really stop giving people the placebo and start giving them the medication. At least that's what our evidence suggests so far. There are, of course, other studies that should be done looking at chemical compositions of your drug and all that kind of stuff. Now, one thing we haven't talked about yet is, of course, effect size measures very much. We talked about the standardized residual, but we can actually look at measures of effect size if we have a 2x2 chi-squared analysis. We'll do that in the next video, so I'll show you how to do that. And then there's some other things you can do regarding effect size for chi-squared. Thanks a lot. I'll see you then.